I'm Anil Kumar. In this video, I'll discuss in details how to sketch graph of given functions. I've taken very simple example, a cubic function to begin with. We'll have three variations to this cubic function. You need to sketch graph of x cubed plus 3x plus 4, x cubed minus 3x plus 2, and minus x cubed plus 3x minus 1. Now, before we really get into details, let me say, what are basic things which we should be looking into? First thing which you should be concerned about is type of function, right? So here we know the type of function is a cubic polynomial. Now, when we know it is a cubic polynomial function, we actually know a lot of characteristics. Characteristics which will come to your mind are that they are continuous functions, right? Since they are continuous functions, we will not work out on their asymptotes and holes and everything. Perfect. What is more important now here is to work on end behavior. So for any polynomial, end behavior becomes important. The other things which we look into is what can we get out of the first derivative, let me call f dash x, and what can we get out of second derivative. We need to analyze these two derivatives to find maximum minimum, point of inflection, concavity, right? So first derivative will give you maximum minimum, which you can say turning points. And the second derivative will give you concavity and point of inflection, right? So these are critical things. Now, to sketch a graph very accurately, we may have some additional information, right? So in that additional information, I will write intercepts. We could have x-intercept. Now, x-intercept only if it is easy to find. Only if easy, not otherwise. The other thing which is very easy to find is y-intercept. Correct. That is, just substitute 0 here. We know y-intercept of a is 4, for b is 2, and minus 1 for c. Perfect. So these things, in short, will help us sketch a good graph. And with these three examples, we will actually see how. Perfect. So let's begin with the very first one. So what we have here is x cubed plus 3x plus 4. As we said, it is a polynomial odd degree. So when it is odd degree polynomial, what is the end behavior? Now here, leading coefficient is positive, right? It is positive 1. And degrees 3. That means odd degree. Now, if the leading coefficient is positive, then the graph will be right side up. And if it is odd, both will be at opposite ends. So that becomes the end behavior. So these two combinations give us information about end behavior, which we could write as when x approaches infinity, y approaches infinity. And when x approaches negative infinity, y approaches opposite end to where it was here, it approaches negative infinity, right? So leading coefficient is positive means right up. And odd degree means this is right up, right? And odd degree means opposite ends. Do you see this? They are going like opposite ends. Is that clear? Now after this, what we can do is we can Write down what our y-intercept is. Easy, right? Y-intercept is, substitute x0, we said y-intercept is 4, right? So we know it is at 0, 4. Now, you have to answer this question. Is it easy for you to find x-intercept for this polynomial? Well, we have to try some values, factors of 4 plus minus, if they can work. So what you notice here is that if I write minus 1, for example, then I do get 0. So that means, let's say this is a polynomial p of x, then p of minus 1 is indeed equals to minus 1 minus 3 plus 4, which is 0. So we do get one x-intercept very easily, right? Which is at minus 1, right? Since we got that, we could try to find other x-intercepts. We could, but not necessary, but we got at least one. Now, cubic function will have, since it is going from here to there, it has to cross somewhere. So for the time being, we'll just work with this one x-intercept, okay? Now let's try to analyze the second derivative. Right? So what we have here is a function y equals to x cubed plus 3x plus 4. Let's find the first derivative, which is 3x squared plus 3. Now, critical points are at this point when y dash is equal to 0 to find critical number, right? Now, since it is 3x squared plus 3, it is never 0. So what we get here is that there is none, right? So there is no critical number. Do you see that? So we find none. Since this equation is always greater than 0, right? Okay, so let's move on and find the second derivative. Don't get confused at this stage. Don't stop here. Move on. Find the second derivative. Once you find the second derivative, you get 6x and equate this also to 0. So if you equate this to 0, what do you find? Well, this is 0 for x equals to 0. So you do get a critical number for second derivative. So since we have second derivative 0 at a point, let us analyze it. So we'll analyze the second derivative. We have 1, 0 for second derivative, which is at 0. So you take a test point on the left side, could be minus 1, and on the right side could be plus 1, and check the second derivative. So we are checking the second derivative, 6x. If it is negative, you'll get a negative value, minus 6, right? And if it is positive, you get positive value. Positive means the graph of the function y or f of x is concave up, and negative means you have concave down. So at 0, we have point of inflection. Do you see that? The concavity changes. Correct? So what we can do here is, we already know at 0 the function is at 0.4, right? That is your y-intercept. Now based on this information, and what we already got is at minus 1, we have a 0, right? This is at minus 1, we have a 0. We could actually draw our function. So let me sketch the function. Now this is point of inflection where the curve goes like this. Do you see, like a, and the concavity has to change, right? So let me make a curve here. Is concave down. So this is concave down. Do you see that portion concave down? Up to 0 from minus infinity. And after this, it is concave up. So that becomes your graph for the given function. Do you understand? It is fairly accurate graph. Let me call this as y. If you really want some more points, what you can always do is find the value for, let us say, x equals to 1, right? So if I plug in 1 here, so I get 1 plus 3 plus 4, which is 8, right? So we get 1, so the point B could be, let's say, we can call this as 1, 8. Is it okay? So once you have this point, so of course this is going to be much steeper than what I have drawn. But once you have a graph paper, you could fairly accurately sketch this curve. So this is how it is going to look. Is that clear? So what we added here is one more point. That is, at x equals to 1, y is equals to 8, right? So we included that point here in the graph and got fairly accurate result. Now let's move on to the next curve. Now we'll write this as a function f of x equals to x cubed minus 3x plus 2. Again, we know the end behavior, right? So the end behavior here is leading coefficient positive means right side up, odd degree means opposite ends. Does make sense to you? Easy, right? Now, y-intercept, that is to say, let me write here, f of 0 is what? So when I substitute 0, I get 2. So y-intercept is 2. Now can I figure out some zeros? If I substitute 1 here, what do I get? What is f of 1? So if I substitute 1, I get 1 minus 3 plus 2, which is 0. So I do get at 1 x-intercept, right? I could actually find the other x-intercept also by dividing this equation. Is it okay? But for the time being, we'll skip it. We'll just move forward. So, and there is a reason for doing so. That is to say, we might get an idea to try another value as we find its first and second derivative. So let's first find the first derivative. First derivative is 3x squared minus 3. Now that gives you 3 is common. We get x squared minus 1. So we do have critical number here, right? So let's figure out the critical number. Critical number is when the first derivative is 0 or does not exist. It is 0 for x equals to plus minus 1, correct? So that gives you critical number as x equals to plus minus 1. So there are two critical numbers. Let us analyze both of them, okay? So we'll analyze both these critical numbers. So that is, we have the first derivative, which is 0 at minus 1 and at plus 1. So let us take a test point. So let us say that the test point here is minus 2. Here we could have 0 plus 2. And what do we have to test? The derivative, which is 3x squared minus 1, right? So let's test 3x squared minus 3. Now, if I have a value which is like minus 2, then what do I get? When I substitute minus 2 here, I will get a positive value. If I substitute 0 here, I get minus 3, which is negative. If I substitute plus 2, I again get positive value. So that really indicates that the graph of the function f of x is positive means increasing. Do you see that? Negative means decreasing, positive means increasing. So that clearly indicates that on the function, I have local maxima and local minimum, right? So local maximum is at minus 1 and minimum is at 1. Do you see that? So let us find the value of this function at both minus 1 and 1. At 1 we have the value. So let's calculate at minus 1. So let me write here itself. So if I write minus 1 here, I get minus 1 and then you can use calculator, right? So minus 1, this becomes plus 3 plus 3 plus 2, 4, 4 minus, 5 minus 1 is 4. So we get a point which is minus 1, 4. So at minus 1, we have a maximum. Let's say this is the point. Let me show it like this. Minus 1, we have this point at 4. We already found that at 1, we have 0. So let's say this is 1 and 0. Now let's analyze the second derivative. Second derivative is, okay, so let's write second derivative here. 3x squared minus 3 gives us, let's say equals to 6x. Now again, the critical number is at x equals to 0, right? X equals to 0 is critical. So let's analyze this. So we can analyze right here, second derivative, which we know is 0 for x equals to 0. So if I take a value which is on left side minus 1 and the right side as plus 1, what I notice is that second derivative is going to be negative on the left and positive on the right, which really means that the function is going to be concave down on this side and concave up, leading to point of inflection at 0, right? So we have a point of inflection at 0. So that means the concavity truly changes at 0, right? So this half of the curve, like this half is very clear, right? So it could be kind of like this. Is it okay? And here, the concavity is changing at 0. So it comes like concave down and then moves concave up. Do you see that? So that is how your function is going to be. Now you have an idea that somewhere here, this point is minus 1, you could have a 0. Is that right? So what you could do is try some values. For example, minus 2, right? So in any case, for accuracy of the graph, it is a good idea to try some values. So we'll try the value of minus 2. So minus 2 cube is minus 8. Minus 2 times 3 will give us plus 6. And we have plus 2. So that is indeed equals to 0. So we get this point as minus 2. So while working for some additional points, we get our x-intercept also. So that's a bonus, right? So let's keep that and continue, right? So we get our graph fairly accurate as shown here. So what you see here is that minor differences with plus and minus in between makes a huge difference. Earlier, we did not have a turning point like this. We did not have any local maximum or minimum. Here we have all that, right? So we have here a local maxima at x equals to minus 1, value being 4, and at 1 we have local minimum with value of 0, right? Now, I'm leaving the last question for you to solve as an exercise. Perfect. Broadly speaking, you can see for yourself that here we have negative leading coefficient, correct? That means right side is down, right? Negative leading coefficient. And this is up. Perfect. So that is how it is, and the graph crosses y-intercept being at minus 1. Analyze first and second derivative and get your graph. So this is for you to practice. Is it okay? So it is a practice question for you.